Most of the time, the radar data we see is dominated by returns within the main lobe, and these side lobes have little impact on the overall output. But sometimes returns within side lobes dominate the total signal, as in this example here, where the side lobe features a much greater preponderance of hydrometeors, including rain and large hail, than the main lobe. This induces an artifact called side lobe contamination. Again, most of the time, side lobe contamination is not an issue, but it can be a major problem in regions with sharp changes in reflectivity, either horizontally or vertically. As it relates to storm chasing, a textbook example of this is in the inflow region of a supercell, which often features a strong vertical reflectivity gradient. Side lobe contamination manifests itself in velocity data as an erroneous area of rotation that can mimic a strong mesocyclone or tornado vortex signature, but is displaced from where rotation should be located within the storm. In other words, a side lobe contamination-induced couplet will not be co-located with a supercell's hook echo or rear flank. Side lobes are also the reason why ground clutter occurs, as they interact with objects at the ground rather than the main lobe. Let's take a look at an example. At first glance, it appears that a tornado may actually be in progress. We have a bona fide supercell, complete with well-defined hook echo and a strong, tight velocity couplet. However, upon closer inspection, notice how the velocity couplet is located in the inflow region of the storm, much closer to the edge of the forward flank. This is a classic sign of side lobe contamination. If this was a tornadic couplet, it would be located back in here, coincident with the tip of the hook echo. Also, note the lack of reflectivity in the vicinity of the couplet, but as we go up to the next tilt, we see strong reflectivity in this area, indicative of a strong vertical reflectivity gradient. This is evidence that the side lobes of the beam at the lowest elevation angle were encountering a much greater concentration of hydrometeors than the main lobe. Here's another example. Once again, we have a classic supercell with a well-defined appendage and a very strong velocity couplet. However, the couplet is located in the clear air well out ahead of the appendage, so this is side lobe contamination. In some cases, side lobe contamination can occur in tandem with legitimate rotation. In this example, we see two potential areas of rotation. The one on the left is co-located with the supercell's appendage, evidence that it's a legitimate rotational couplet, while the one on the right is side lobe contamination, situated in the storm's inflow region just south of the forward flank. You can see how easy it is to be fooled by one of these erroneous couplets, so always make sure that the velocity couplet in question is real when you're analyzing radar data. This graphic from Betcher and Bentley 2022 gives a good workflow for diagnosing whether or not a circulation is legitimate or associated with side lobe contamination. Couplets induced by side lobe contamination will be misplaced from the hook echo or rear flank of the storm, typically with weak to no reflectivity in and around the false circulation. Although imposter couplets can mimic a tornado vortex signature fairly well, they also frequently take on a blocky, disorganized appearance that lacks a clear velocity gradient. Finally, there will be a tilt or tilts of enhanced reflectivity above the imposter couplet, which is evidence of ample hydrometeors for side lobes to sample.
Don't learn storm chasing alone. Go where chasers are already talking. Discord community link in description.
The final artifact we're going to discuss is called a three-body scatter spike, which is a telltale sign of large hail. When the radar beam encounters large hail within a storm, part of the energy within the beam can get deflected down to the ground, back up into the storm, and then back to the radar. It gets deflected 3 times, hence the name three-body scatter spike. This portion of energy arrives back at the radar slightly later than the original backscattered energy, so the radar assumes that it exists farther along the radial than the storm itself. The result is a spike of low reflectivity that extends along the radial outward from the storm's core. Three-body scatter spikes are also often accompanied by significantly decreased correlation coefficient. On rare occasion, damaging tornadoes can produce a three-body scatter spike as the radar beam deflects off of heavy lofted debris. In these cases, the three-body scatter spike will emanate from the debris ball at the tip of the hook echo in reflectivity.
Remember to check out those links in the description below, and then watch another video.